Hello students, today we will start with store and forward networks and how it is going to work. So let me show animated representation of how the packet is frame is forwarded from the store and forward network, right? So if you see here, it is calculating the CRC, which is nothing but cyclic redundancy check. If there is no error, the packet is forwarded to the destination, right? So first PC1 is the host, and it is calculating the CRC value and it is inserted in the header. So second, it is in the router. It is checking whether there is no error. If there is no, in the switch, it is checking whether there is no error. If there is no error, it will be forwarded to the destination, right? So this is the working of store and forward networks, right? If the CRC is nothing but we have already discussed about error control, right? So CRC, cyclic redundancy check, is a technique which is used to check whether there is an error in the frame or not, right? So that is what given here, CRC. CRC is nothing but cyclic redundancy check, which is used in data link layer as error detection technique. Right. So if you see here in the store and forward network, this is the frame what we are representing here, right? So frame representation in the local area network will be like this. It will have preamble, destination address, source address, the Ethernet type and data, and then finally FCS is nothing but frame check sequence. That is what we have represented in the previous diagram as CRC, right? So it is used for error detection, right? So this is how a particular frame looks like, right? So this is the data what you are going to insert, and remaining part and all header information, which includes preamble. Destination address is nothing but MAC address of the destination, and source address is the MAC address of the source, and what type of Ethernet we are using, and then data followed by error detection technique, which is CRC, which I have showed an example in the previous diagram, right? So what it is going to do, it will not just forward it, it will store the content in the switch, then it will forward it to the destination. That is known as store and forward network. So now we will see the theoretical concept of store and forward network. So a store and forward network is a type of network where each intermediate device receives the entire packet. So intermediate device is nothing but what we are representing here as switch. So it receives the entire data packet, store it temporarily, check it for errors, and forward it to the next node. So as of now, what we have represented here it is as frames, right? So you can represent as frame itself. So it receives and stores the entire data frame, stores it temporarily, check it for errors. If there is no error, it will pass to the next node. This process repeat until the frames reaches the destination, right? So this is what how store and forward networks works. And how it works, the step-by-step procedure is shown here. Sender divides the data into packets or frames, and the packet is sent to the next node. Node stores the full packet. Error checking is performed. Packet is forwarded to the next node. Right. So mainly operates the store and forward either in the data link layer, that what we have represented as frames, or in the network layer, which is represented as packets, right? So example for store and forward network, internet packet switched networks, internet switch, ethernet switches, store and forward switching, email system, classic store and forward messaging, right? So email system, it is not directly forwarded to the recipient, it will be stored in the server, then only it will be forwarded, right? So packet switched network, store and forward switching in Ethernet switches. These are the real-time examples. So now let us see the difference between. So there are two methods for forwarding the frames or packets. So one is store and forward, what we have seen in detail, and then another one is cut through switching. So in this cut through switching, we will see what is the difference, right? So the feature is packet reception. Store and forward will forward the entire packet. Cut through will forward only the partial packet, not the entire one. Error checking is, I have shown a demo how the error is checked. It will do error checking, yes. And here cut through, it will not do error checking, it will just forward it. Latency is higher because we are checking the error, then only we are forwarding the frame or packet. But in cut through, the latency is lower because no processing in the intermediate devices are carried out. And reliability, it is high reliable, and cut through is lower. That is also because of error checking is not performed in the cut through. Usage, most modern networks, high speed, low latency LANs or use this store and forward networks, right? So the analogy of store and forward and cut through is given here. Post office receives the full letter, checks the address, then send it to the destination. But cut through, courier starts delivering after reading only the destination address, right? So that is what, right? So with this, we are completing store and forward network. Next, we will move on to the performance metrics. Okay, next we are going to start with network performance metrics. So let me present the slide for that, right? So these are the different features or parameters that are affecting the network performance. Let us see each one, right? So throughput is the first parameter, and then packet delivery ratio. Throughput is nothing but how efficiently the data are reached to the destination without noise destruction, right? So that is what throughput. And packet delivery ratio, and then a delay, that is end-to-end delay. Which protocol is which layer is providing end-to-end connection, that is transport layer protocol, right? So end-to-end delay is also relied on this transport layer protocol. And if there is any overheads, right, like noises or interference, whatever it may be, that also affects the performance of the network. And then route discovery rate, if the route towards a particular destination is not discovered properly or efficiently, then that delay will also reduce the performance metrics. And then next is packet loss rate, how many packets you are sending and how many are receiving properly, that determines the packet loss rate. And then lifetime, packet lifetime, right? So that's, there will be a certain hop counts, only for that hop counts the packet should be live in the internet. Otherwise the packets will become zombies and it will start occupying the internet, and the bandwidth of the network will be reduced, right? So the lifetime of the packet should also be uh, properly mentioned, otherwise it will increase the performance of the internet. Okay. So now let's see what is node, what is a link, right? So this host and all represented as node. Similarly, intermediate devices like switches, so consider this as switch, right? And this is router and this is another switch. Or you may consider this as router also, switch or router, right? So all these devices, right? So this is also represented as nodes. This is also represented as node. This is also represented as node, and this is also node, right? So whichever node that is capable of processing the packets, that and all known as nodes, which is available in the network. And the link between the connection between the nodes is known as link, right? Node is nothing but the system which is capable of processing the packets or frames is known as node. A link is nothing but the communication between the nodes, right? So that link can be either wired or wireless, right? So that is what represented here. Excuse me. So next is how the node is processing, right? So already we have seen an example in store and forward. It is checking for the error in the switch, and then only it is forwarding to the next node, right? So that is known as processing. Whenever there arrives a frame or packet, that will be queued in the node, and it will start processing each frames one by one, and then only it will start transmitting, right? So this is what the node structure, and this is what the link structure, right? So the link consists of the frame to which consists of data information like header information as well as the data. So to which node it has to transmit, right? So that is what transmission, and then the propagation delay is occurred in this link. Propagation delay is nothing but starting from the source node to destination node, how much delay it requires, time requires, that is known as propagation delay. So next we will see the causes of packet loss, right? So there are several causes due to which the packet can loss. So first one is misconfiguration, right? So configuration of packets, or if it is not configured properly, then that will lead to this packet loss. Second one is faulty connection, right? So if there is any connection error between the source and destination, that will also cause packet loss. And then unwanted traffic, right? If there is any congestion in the network, that will leads to traffic, that will leads to packet loss, right? So congestion is nothing but the bandwidth of the network is fully occupied with packets, and the packets cannot move to and fro to reach the destination, right? Similar to traffic in the roadside, right? So if you see there is a the if there is a four corner representation of roads, right? And the traffic will be heavy in the center, right? So similar to that, if the traffic in packets are heavy, automatically it will leads to lost packets in the network. So next is outdated devices, right? So some of the devices in the internet, if it is outdated and if it is not supporting the speed which is available by other devices, that delay will also reduce the that delay will also induce a packet loss in the network, right? And then next comes DOS or DDoS attack, right? So DOS attack is we are sending so many number of flooding packets towards the destination, that will leads to this DOS attack, right? So if there is DOS attack, original packets from the authorized users will be lost, right? So next comes more data. So that is this is also overloading of the application, right? So if there is more request from the users that which cannot be handled by the destination, then there will be a packet loss, right? So if you see here, these three green packets are reached successfully, but this red packet is deleted because of overloading of the network. And then the distance, right? So the distance between the source and destination, if it is large, then that will also that is also a possibility. There will be a possibility to remove the packets from the network. Next is software issues. If there is any software misconfiguration or issues, that will also reduce the that will also delete the packets which are available in the network. Okay, now let's come into the picture where the content in the syllabus is mentioned. The network performance metrics are used to evaluate how efficiently and reliably a network delivers data. So the most important metrics are throughput, delay, jitter, and drop rate. Right. So first we will start with end-to-end throughput, right? So what is throughput? The definition of throughput is given here. End-to-end throughput is the rate at which data is successfully delivered from the sender to the receiver over the network, right? So, for example, if you are sending 10 Mbps of data, right, and this 10 Mbps of data, if it successfully reaches the destination with the rate of 10 Mbps, then it is 100%. It is throughput is 100%, right? So that is what we are representing here. Rate at which data is successfully delivered from sender to receiver over the network is known as end-to-end throughput. And the formula for throughput is given here: total data received divided by total transmission time, right? So this is the throughput at receiver side. Sorry. So how much data it is receiving divided by total transmission time, right? So this throughput is measured in bits per second or megabits per second or gigabits per second, right? So so the throughput is limited by bottleneck link. So bottleneck is nothing but if there is more congestion. If you consider a bottle, so let me draw it once again. I think you all have gone through how a real time bottle looks like. So there will be a narrow edge, and the bottle will be like this, right? So consider this as a bottle. So in this narrow edge, what we are representing, whatever flow from this from this base to the neck, this is known as bottleneck, right? So obviously, if more flow is there in this bottleneck, there will be a congestion in this, right? So that is what bottleneck. So similarly, if the packet is traversing from higher bandwidth towards a lower bandwidth, then there will be bottleneck in the link, and that will reduce the throughput. So there is an example for a solved problem for throughput here. If 10 MB is received in 5 seconds, then the throughput is 16 Mbps, right? That is 16 megabits per second, right? So now let's see how this is calculated. So we know 1 byte is equal to 8 bits, right? So now 10 MB, so if it is capital B, byte, right? If it is small b, it is bit. You should be careful by representing the b, right? If it is capital B, it is byte, and if it is small b, it is bit, right? So 10, so since it is megabyte, we are including 1024 for mega representation. 10, this is the 10, and 10 into 1024 into once again 1024 bytes, right? So you will get a particular value. This value into 8 will be represented like this values, right? So you can calculate it and verify it. So this is step 1, converting the given data into bits. Next is calculating the throughput. So we know throughput is equal to total data received divided by time taken, right? So here total data received is what we have calculated in step 1 divided by time in seconds, 5 seconds, right? So you will get 16 lakh 77,000 sorry 16 lakh so this is the value what we are getting in bits per second, right? So and then we are it is not 16 lakh, more than 16 lakh. So here after converting this to megabits per second, right? Megabits per second, we know 1 megabits per second is equal to representing this here as 10 lakhs, right? So 16 divided by 10 lakhs, sorry, 1 crore 67 lakhs, like that we are representing divided by 10 lakhs, you will get the value as 16 Mbps, right? So hence the throughput is calculated as 16 Mbps. So that's all about throughput. Next we will move on to latency. So latency is end-to-end delay is the total time taken by the packet to travel from source to destination, right? So latency is represented as a delay. It is a total time taken by a packet to travel from source to destination. So the components of delay are processing delay, queuing delay, transmission delay, propagation delay. Now let's see what is processing delay, right? So processing delay already we are represented in store and forward network, how the switch is processing and checking whether the error is occurred or not, then only it is forwarding, right? So that type of processing in the intermediate devices, that is known as processing delay, right? So how this processing delay may occur due to error checking and then header processing, to which address it has to transfer, that type of processing and all occurring in this header processing, right? So if it is data link layer, it has to process the MAC address and it has to deliver to the corresponding intermediate device. And if it is a network layer, it has to process the IP address and deliver it to the corresponding nearby node, right? So next is queuing delay. So queuing delay, we know buffers are used to maintain the flow control, to synchronize the flow between the sender and receiver. So waiting in the buffer is representing this queuing delay. So next comes transmission delay. Transmission delay starting from the source and receiving at the destination, right? So packet size and then the link bandwidth, right? So this is the link between the source and destination. But this link consists of so many number of intermediate devices also, right? So the packet size as well as the link bandwidth divided by link bandwidth represents the transmission delay. And then the propagation delay. So the distance between the source and destination, right? So distance divided by signal speed. What is the speed of the signal? Based on that, the distance covered, based on that the propagation delay is calculated, right? So distance divided by signal speed, right? So there are four types of delays which will induce a delay in this latency, right? So latency consists of these four components of delay. So the formula for calculating latency is total delay is equal to processing delay, queuing delay, transmission delay, and propagation delay. So sum of this all the four, right? So example here important for real-time application like voice and video. Next is jitter. Sorry. So far we have covered throughput and latency. Next we are going to see jitter, right? Third one is jitter. So jitter is the variation in packet delay over time, right? So the variation, so first, while you are transmitting packet in the first duration, if the delay is only 20 milliseconds, and if you are transmitting the next the same set of packets over the same from same source to destination, if it is 30 milliseconds, then this 10 milliseconds, the difference between these two is known as the jitter, right? So jitter is the variation in packet delay over time. So the key points is high jitter causes distortion audio and video. So it is occurred due to variable queuing delays measured in milliseconds. So next is drop rate, fourth one. So that's all about jitter. So millisecond, already I have given an example for that. So definition for drop rate is, it is a fraction of packets that are lost during transmission, right? So we have seen several parameters that are causing for packet loss. I think you remember that diagram which represents different parameters which causes of packet loss, right? So due to this different parameters, the packet should be dropped, right? So that is how many packets are dropped for the packet what we have transmitted, that will be measured in this drop rate, right? So drop rate is the fraction of packets that are lost during transmission. So the formula for drop rate is drop rate equal to packet loss divided by packet sent, right? So for example, if you are sending 10 packets and only 8 packets, sorry, 2 packet is lost over here, so that it will represent the drop rate, right? So buffer overflow, congestion, link failures, transmission errors impact and the impact of this reduce the throughput, causes retransmission. So the retransmission is using TCP, and it represents a severe impact on real time traffic. So next comes Little's law after drop rate. So the formula of Little's law is L is equal to lambda W, where lambda represents average arrival rate and W represents the average time a packet spends in the system, right? So and L is the number of average number of packets in the system, right? So this is how we are representing Little's law. L is equal to lambda W, where lambda is average arrival rate and W is average time a packet spends in the system. And next, application in networks. So for Little law, what is the application in networks? Is used to relate delay, throughput, and queue length, and it is valid for stable system. So now we will see how network performance is measured. So that network performance measurement we will discuss in the next class, right? So that's all about today's class. We have seen certain parameters which are affecting the performance and how that parameters are evaluated, right? So thank you.